Okay, take three. Okay. Hi all, my name is Michael.
And my name is Henry. And together we form a team for our EE4455 Embedded System project.
For our assignment, we have chosen to work on the first example given, which is to design audio equalizer to filter out different kinds of noises from a musical signals.
Without further ado, let us show you the design of our audio equalizer, and we shall see how we can use different ways to remove the unwanted noises given in different parts of the question.
Okay, let's move on to the first question. Okay, let us look at the first part of our project. A musical signal is given with a mix of multiple tonal noises. Our task is to use these MIDEX to perform audio equalizations to clean up the noise. So let's listen to the music first. Okay, as you can hear from the musical signal, there's a constantly humming going on at the background with something like Okay, so firstly, we have to identify where are the noises located in the frequency domain. The equalizer design consists of 7 bands that made up by a set of bandpass and bandstop filters. Bandstop filters are implemented in a series manner to isolate the specific band from original signal. Concurrently, in the parallel implementation, there is also a set of bandpass filter corresponding to their respective bandstop filters. These allow us to customize the center frequency, bandwidth and gain of the different bands. In addition, we have created another 7-band equalizer specifically to solve question 1.2 in suppressing broadband noises. Lastly, we have also kept the original 3-band equalizer from the reference document to fine-tune the audio signal. Okay, here is our front panel interface. There are 2 power spectrum analyzer for input and output analysis. At the bottom, we have a graphic equalizer that allows us to customize the center frequency, bandwidth, and also the gain. By activating this switch, the graphic equalizer will switch to our customized 7-band equalizer specifically for the question 1.2 to suppress broadband noises. Over here, there is a 3-band equalizer retained from reference document, and here is the master volume control. This is the screenshot captured during the playback of musical signals. We notice that at 22 seconds of music, the musical signal toned down, and this gives us a clear indication of the tonal noise, which is located at 100, 250, 500 and 1 kHz. Okay, as previously mentioned, we identify 4 tonal noises exist in the musical signals. Therefore, we have to design a 4-band equalizer to clean out the noise. The design of our filtering system consists of bandpass filters and bandstop filters. This gives us the ability to isolate the signal of the particular band from the original musical signal itself, and give us the ability to perform audio equalizations for the particular bands. The center frequency of individual bands are set to 100, 250, 500 and 1000, which is corresponding to the tonal noise itself. So now let us listen to the original signals. Okay, as you can see, there's a constant peak going on at 1000, 500, 250, which is somewhere here, and 100. So let's listen to the processed signals. And the humming noise is gone. Okay, so in order to solve these questions, we created 4 bands equalizers with a center frequency of 100, 250, 500 and 1 kHz. After going through a few rounds of trial and error process, we noticed that 50 Hz gives us the best result in terms of eliminate the noise while preserve the quality of the musical signals. And lastly, the gain of the frequency band, we try to eliminate as much as possible. So in this case, we will put it as 0. Okay. In summary, this design is actually applicable for all the musical signals that is mixed with tonal noises, as long as you can identify where are the noise located in the frequency domain, so that you can pinpoint the noise and then clean it up.
For the second part of the question, we are supposed to investigate the effect of mixing different kinds of broadband noises with our musical signal, so that the combined signal, after passing through our audio equalizer design, we are supposed to see how we can attenuate the noises to the greatest extent. So the different kinds of broadband noises that are specified in the questions include the white noise, pink noise, and grey noise. But as an illustration, okay, just to investigate the spectral characteristics of the different kind of broadband noise, you can see that, okay, for the white noise, it has an approximately average constant power level, whereas for the pink noise, the power level is inversely proportional to the frequency. But whichever kind of distinct characteristics they differ from each other, the fundamental thing is that broadband noises extends throughout the whole frequency range. And this is actually important in our filter design, because it's going to affect the signal throughout the whole spectrum. So our approach in targeting how to attenuate this noise to the greatest extent is to actually separate the frequency spectrum into different frequency bins. Okay, within each bin, we will investigate, okay, as to the average power level of the noise versus the original music content. If the average signal power is greater than the average noise power, then we will try to reduce the gain to a less extent, because more of the information is contained within this band. Whereas for the other case, if let's say there's greater noise power than the average signal power, then there is no point preserving too much of this band, because mostly it contains noise. So the only question left is to determine how are we going to segment this frequency spectrum, and I'm going to explain this in our graphical user interface.
In answering our question 1.2, we activated a 7-band equalizer which we calibrated, and this implementation is sufficient to attenuate the broadband noise considerably. The starting center frequency was at 125 Hz and approximately doubles for every equalizer lane until the last lane, which is at 12,000 Hz. The bandwidth for each equalizer lane is as shown over here. And we note that for the higher center frequencies, we actually use a larger bandwidth. This is because most of the music signal would have be below 4,000 Hz, and anything after 4 kHz will have minimal music content. Hence, we would use a larger bandwidth to suppress the more dominant noises in these regions. So let us now hear the music coupled with white noise. To suppress most of the noise, we reduce the gain of the higher frequencies. And you can now hear that the music is cleaner now. The next illustration is with pink noise. And you can actually hear that pink noise is suppressed to a greater extent than the white noise. Now, due to time limitation for our video, we will not be able to showcase grey noise, but we would just like to reiterate that the concept of suppressing broadband noises is the same and can be applied similarly to different kinds of broadband noise.
Okay, for the next part of the question, we are supposed to analyze the effect of mixing motorcycle noise together with our music and determine how we can suppress the engine noise to the greatest extent. But before we go about doing so, we must first identify what are the characteristics of engine noise. Okay, because of the nature of the motor, which is firing at revolutions per minute, the sound spectrum is actually cyclical in nature. And the main characteristic we target to reduce the noise to the greatest extent is actually based on its fundamental frequency and its harmonics. Other kinds of characteristics displayed by the waveform can be contributed by the formant frequency, which is actually the resonance frequency from the exhaust pipe, or its anti-resonance frequency. All these kinds of characteristics actually contribute to the sound waveform from the engine noise. But the ones that we target to reduce the sound from the engine noise to the greatest extent is actually its harmonics and its fundamental frequency. So if we were to look at the spectrum, we just have to identify the peaks and set our filters at these center frequencies with a reasonable bandwidth, such that we can reduce the noise to the greatest extent.
Okay, so let us now analyze the frequency spectrum of the engine noise. As you can see over here, there is a spectral peak at about 125 Hz, and this is likely attributable to the fundamental frequency of the engine noise. What we are going to do is to use this as our guiding principle to determine the center frequencies of the different filter banks that can effectively eliminate the engine noise to the greatest extent. But before that, another characteristic you can see is that approximately 600 Hz and beyond, the spectrum of the engine noise falls to a relatively low power decibel level. Hence, we decided to leave this region untouched and unfiltered, since it is not going to affect the music signal extensively, and in doing so, it will actually preserve the original music content. Moving on to the filter banks, the first filter was set at a center frequency of 125 Hz, corresponding to the fundamental frequency of the engine noise. Successively, the harmonics at 250 Hz, 375 Hz, and 500 Hz, not extending beyond 600 Hz, were also used. On top of that, we also calibrated another band at 62.5 Hz, so that we are able to clean out some low vibrational noise. The bandwidths are shown over here and ranges about 100 to 200 Hz. But as for the gain, as fast as possible, we have kept it to the minimum level of 0, but for bands 3 to 5, we have kept it at around 0.3 or 0.55, so that we are able to establish some kind of trade-off to maintain some original music signal while suppressing the noise considerably. So now let's turn on the filters and listen how much the engine noise has been cleaned out.
50 miles an hour.
As you can hear, a lot of the engine noise has already been cleaned out. So coupling the original engine noise with the music signal and turning on the filters, you can hear that a lot of the engine noise has been cleaned out and most of the original music signal has been preserved.
Okay, so now let's look at the last question to examine how the masking effect can help to mask out the tonal noises. So, what is masking effect? Masking is an effect that with the original signals, the presence of stronger signal will render the weaker signals to become inaudible. So in this graph, humans have this hearing threshold where you can see this red color curve, whereby any signal that goes beyond the level, the signal is audible by our human ear. However, with the presence of stronger adjacent signals, the hearing threshold will now increase, and these original signals will become inaudible because it is now below the hearing threshold. To further illustrate our ideas, we choose 1 kHz tones as an example because the 1 kHz tones is also the most significant tones exist in the musical signals. So let us look at the masking skirt. In this diagram, masking skirt shows that it can mask out more higher frequency components than lower frequency. So based on this concept, we decided to choose the lower adjacent signals to be a masker to mask out the 1 kHz tones. But after going through a certain amount of testing, we realized that this masker is not sufficient to mask out the signals due to the fluctuations of the signals. Therefore, we decided to use the higher adjacent signal, which is 1.1 kHz, to complement the 900 Hz masker with a significant gain increase.
So based on the masking theory that we have mentioned, we now use 1 kHz tones as example to illustrate the idea. Since the masking effect is more significant at higher frequency, we choose 900 Hz as masker to try to mask out the 1 kHz tones. So let us listen to the signal with masker tone at 900 Hz. Okay, we notice that the result is not significant because the frequency content in 900 Hz band is not sufficient to mask out 1 kHz tones. Therefore, we try to utilize the higher frequency as masker. In this case, we use 1100 Hz, and here is the result. These produce a better result as the 1 kHz tones is now perceptually become less significant to our human ears. These two maskers are able to compensate with each other since the frequency content in these two bands are not consistent. So this is the best result we can achieve, and we apply the same approach for the rest of the tonal noise.
Okay, lastly, for question 1.5, we are asked to investigate other noise cancellation methods whereby we do have some ideas in mind, but we couldn't implement into a prototype program. The idea are such as peak detection, where we're thinking to use the LabVIEW program to do a peak detection by on the spectrum itself. And also another method will be a 180-degree out-of-phase cancellation. The left channel will use to generate original signal with noise, and right channel will be used to generate the phase inverted tonal noise to cancel out the noise in the original signal.
Okay, so now moving on to the summary. Okay, for our project, we have actually investigated with different methods whereby we can remove noise from the original music content, and this is demonstrated through the 4 exercises, whereby for 1.1 we investigated with tonal noises, for 1.2 we played with broadband noises, and for the third exercise we actually tried to attenuate engine noises. Then as a last exercise we also performed some form of auditory masking to actually see how we can mask away tonal noises. Yes. Okay, so with that in mind, I think we completed our project. Yeah.
Okay, so thank you for your 15 minutes to walk through our project. So yeah, that's all.
Okay.
Thank you for your time. Thank you so much.
Oh, wait. One thing. Yeah. Okay.
One last thing. Okay. One,
2, 3. Prof Gun, we love you!
My girlfriend's gonna kill me like that!